Hello again. This is Math 2134 coming to you from the College of DuPage. The title of this lecture is Integration Applied to Computing Volumes of Solids of Revolution. Again, I remind you to be an active learner while you watch this video. This aligns with this section in your book, and our objectives are to find the volume of a solid of revolution using disks and find the volume of a solid of revolution using shells. By way of introduction, then, what we're going to do is we're going to have a function y equals f of x. That's this red line. But then what we're going to do is we're going to take the x-axis as the axis of revolution, and we're going to be revolving this function from x equal a to x equal b around this axis of revolution. So you can think about that as holding this axis in one hand and spinning the function around. And we get this going around and around and around. So we're trying to find the volume of this expression then. And it is going to be a solid, and in fact there's a name for this. This is called a frustrum. Well, we don't need to know that, but what we can say is, oh, the area under here could be approximated by taking slices along the way and seeing what happens with a slice. And so what we're going to have is that this is approximated in much the way we approximate Riemann sums by having a value here, 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 where we're taking f to be constant, and then we're going to have a uniform distance along here, which is delta x. So you see each of these is going to be a disk, and the disk is going to have a top, there's a bottom, and there's a height. So the area of the top times the height is going to be, that's the area of the cylinder. So we're going to say, what is the area of the top? Well, the radius of the top is going to be at f of x sub I is greater than or equal to 0. And that's the radius at that point. That's where it goes around. And this radius is very close to the same, and we're assuming that that is flight, is the height, that's the depth, so that is delta x. So you see, since the volume of a right circular cylinder is given by volume, this volume is equal to pi r squared h, then the volume is the area of the base, which is pi r squared, times the height. And then we're going to be adding up all of these. Now each of the approximating disks then has this volume. And squaring allows for cases where it's less than 0, but f of x is always the distance from the axis of rotation, and so we're squaring that. So the volume of the solid is approximated by the sum of all the volumes of the disks. We just add them up. Now the actual volume is the limit of this sum as the thickness, height, of each disk, delta x, approaches 0. And that means that the number of disks approaches infinity. So this volume is going to be the limit as n goes to infinity of the summation I equal 1 to n pi f of x sub I whole squared times delta x. But in this limit we know that this is the definite integral, so this is pi, the definite integral from a to b, f of x whole squared dx. That is, the volume is the value of the definite integral of the function y equals pi f of x whole squared from a to b. And that gives rise, and in fact is a proof of the following theorem, volumes by disk. So let's suppose we have a non-negative continuous function f defined on AB. The volume, V, of the solid of revolution obtained by rotating the area under the graph from A to B around the x-axis is given by the volume is equal to pi, the integral from A to B, f of x whole squared dx. Examples are worth many words, so let's do an example. So we want to find the volume of the solid of revolution generated by rotating the area under the graph of y equal the square root of x from x equals 0 to x equal 1 around the x-axis. So here is the x-axis, And here is the function. The red one is y equal the square root of x. We're talking about the area under that from 0 to 1, and we're spinning it around the x-axis. So we go around, and we get this. Now this is just this point here, but it gets wider, so you see we get this paraboloid kind of a shape. And from the theorem we know this volume then is going to be equal to pi, the definite integral from a to b, f of x whole squared dx. So we're going to go from pi, x goes from 0 to 1, that was dx, and f of x was the square root of x, that's x to the 1/2. So what we're going to do is, but we're squaring x to the 1/2, so we get x. So we're integrating pi, the integral from 0 to 1, x dx. We add 1 to the exponent, divide by the new exponent, and use the fundamental theorem of calculus to evaluate this. We find that this volume, excuse me, not area, this volume is pi over 2. That is the exact volume. Here's another example. Find the volume of the solid of revolution generated by rotating the region under the graph of y equal e to the x. Now here's the graph y equal e to the x. Here's the x-axis and here's the y-axis. We're drawing this at an angle so we can actually see the revolution. So what we're doing is we're revolving this function and the area under this function all the way around. So it gives us this volume. It looks like a horn of some kind. And we're finding that under the graph of y equal e to the x from x equal -1, which is way over here, to x equal 2. Okay, so by our theorem we know that the volume is equal to pi, the definite integral from a to b, f of x whole squared dx. Now this is e to the x, and we're going from -1 to 2. And e to the x whole squared is e to the 2x. Now we do have to do a change of variable here. We're going to let u equal 2x, but when we do that and do the integration, and you should verify these calculations, we're going to get as the integrand pi over 2 e to the 2x, and it goes from -1 to 2. So we're going to use the fundamental theorem of calculus to evaluate this. So we'll substitute the top integral in, the top value in, minus the bottom value, and so this is going to be pi over 2 times the quantity e to the 4th power minus e to the -2. That's the exact answer, and if you plug this into a calculator, you will get around 85.55. You should verify all of these calculations. Let's do a very applied example. We're going to talk about water storage. Now, this water tower is used to store water, but is found by taking a function f, and that looks like this. But this time, we're going to rotate this around the x-axis. So we're doing this and going down here. So you see we get a shape that looks like this. So the interior of a university's water storage tank has the shape of a solid of revolution generated by rotating the area under this graph. Then this is the ellipse, so that's the area under the graph, and we're rotating it around here. We're going from -40 to 40. So we're getting an elliptical kind of thing, and that will have a volume. So what is the volume of this tank? Well, I showed you the graph, and here's the picture, so that is all good. And so what we're going to do is, and here it's suggesting that we can simplify our calculation by going from 0 to 40 and realize that the whole thing is going to be twice that. Okay? So because this area is the same as the area that we have over here. And that's something we learned to do back in a previous chapter. So if we rotate that, then we're going to go from 0 to 40. And you might say, well, why would we do that? It's going to be an easier calculation when we use 0 and 40, rather than using -40 and 40. So the volume is equal to pi. We're integrating from 0 to 40. And here is the function, whole squared dx. Now when we square this, we're going to be squaring both of them. So we're squaring 50 to get 2,500, and we're squaring this business square root to get this. So that's the thing that we're going to be integrating. So we're going to go through then and integrate this. And so what we'll get when we integrate that is, so when we integrate the 2500, we get 2500x. When we integrate this, we add 1 to the exponent, divide by the new exponent. And so we'll get 25 over 48x cubed. We'll evaluate it at the top and the bottom, and we'll subtract, and we'll get this. Now we have to multiply this result by 2. That'll make that 400,000 over 3 pi. That's the exact answer, and when we substitute an approximation for pi, we get approximately this many cubic feet. Now, since 1 cubic foot holds 7.48 gallons, this tank holds over 3.13 million gallons of water. Now, there's another way that we can do this, and that is called volume by shells. And this time, what we're going to do is we're going to take this function, y equals f of x, and the area underneath it, but now we're going to be spinning it around the y-axis. And so we're spinning that around the y-axis, and we're seeing what that gets. And again, we get a series of cylindrical shells. Now, when we look at what each one of those shells is going to look like, we'll see that it ends up being a cylinder. Now, the side of this cylinder then is going to be 2 pi, and it's times x1, and this is going to be f of x, and then we're going to have a delta x as well as it changed. So the volume of the ith shell is length times height times width, and the length was 2 pi, and that's really r, times f of xi times delta x. So when we add those up and take the limit as n goes to infinity, we get the definite integral. But you notice it's a different formula now. The volume then is going to be this limit as n goes to infinity, and in the limit that's going to be 2 pi, the integral from a to b, and this is going to be x f of x dx. Giving rise to the following theorem. So, and this is the volume by cylindrical shells. Let R be an area bounded by the graph of y equals f of x, the x-axis, and the lines x equal a to x equal b. If R, that region, is rotated around the y-axis, the volume of the solid of revolution is given by volume equal 2 pi, the definite integral from a to b, x times f of x dx. Again, an example is worth 1,000 words, so let's look at the example. Find the volume of the solid of revolution formed by rotating the area under y equal x squared plus 1 over 0 to 6 around the y-axis. Okay, by the theorem, we know it's going to be, this volume is going to be 2 pi, the definite integral from a to b, x times f of x dx. So that is 2 pi. We're going from 0 to 6. And the f of x is x squared plus 1, but I'm multiplying by that x, and we're integrating dx. Now you do algebra here, I just distribute this, so I will get x cubed plus x. And now I'm going to integrate this. I add 1 to the exponent, divide by the new exponent. I add 1 to the exponent, divide by the new exponent. I use the fundamental theorem of calculus to evaluate that. So we evaluate it here, and we get that the exact answer is 684 pi, and that's volume. Okay, to summarize then this section, we can find volumes by disk. So if F is continuous on AB, then the volume of the solid revolution formed by rotating the area under the graph of y equals f of x from a to b around the x-axis is given by volume is equal to pi, the definite integral from a to b, f of x whole squared dx. Now realize here that the cross-section in this case is pi r squared delta x, and the cut is perpendicular to the axis of revolution. We also learned about volume by shells. So if F is continuous on AB, then the volume of the solid revolution formed by rotating the area under the graph of F from A to B around the y-axis. So this is going to be around the y-axis, is given by the volume is equal to 2 pi, the definite integral from A to B, x times f of x dx. Now here you will note that the cross-section is different. This one is 2 pi r h. And so this is what we get for that, is 2 pi r delta x. And the cut is parallel to the axis of revolution. Now, sometimes either the disk or shell technique is easier than the other one. And this can be a compelling reason to have the two approaches. When both approaches are viable, they will give you the same results. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.